Hello, I'm Kiera Augusto, and this past summer I had the opportunity to work under Dr. Jeffrey Martin through the University of Winnipeg looking at a liquid deuterium thermosyphon for an ultracold neutron source. My main objectives were to numerically simulate and to determine the optimal geometry of the heat exchanger, or HEX, and to further understand how a thermosyphon works, and specifically with those two goals, looking at how temperature and mass flux change with time and space. Eventually, this entire loop will lead to the cooling neutrons at Triumph. And by cooling those neutrons, we hope to measure the electric dipole moment way more precisely than we ever have been able to. And then through that, discover a new source of particle-antiparticle symmetry violation beyond the standard model of particle physics. To do this, the Toucan collaboration is building this ultracold neutron source at Triumph. As you can see in figure 1 over here, that's a pretty realistic model of the total proposed thermosyphon and shielding that will be built as when I last worked on it. So what is a thermosyphon? A thermosyphon is a natural circulation system. So as you can see in figure 2, the schematic drawing I have of a basic thermosyphon, the cold liquid will start in this blue box here. It'll fall down and over, then into this hot box, this red box. Since the cold liquid is much denser than the hot liquid, it'll push the hot liquid up and over into the cold box and continue cycling around like that. Thermosyphons are really good because they're much cheaper and they're much safer than, for example, putting a pump in. So the two main geometries of hexes that I looked at were, as you can see in figure 3, a straight rectangular finned model, and figure 4, a helical finned model. Finally, as I was working through the summer, I had to make my model much more realistic than it started out. So it did start out as this square loop, which is not all we want it to look like. I eventually made it the loop look like figure 5, but in a 1D version of that. We also ended up adding friction factors. As the liquid flows through the pipes, it is impeded by friction. We added heat conduction through the walls and along the walls, specifically also because different walls are different materials. There are steel and aluminum ones, so that has different thermal conductivities, which changes how much heat's getting through. And finally, we checked a bunch of the approximations that were made from the equations that I started with. So specifically in the original equation taken from VIG-IN, the mass flux should be proportional to Q or power to the 1/3, and the temperature should be proportional to Q or power to the 2/3. Even with all of my specifics that I put in relating to my model, the powers were still in excellent agreement with 1/3 and 2/3, so that I was on the right track. Finally, with my results, as you can see over here, the first graph in figure 6 is mass flux as a function of time. It ends up plateauing at about 3.5 grams per second, which is very close to what we figured it was going to be. And in figure 7, that's temperature as a function of time, and it plateaus out the hot temperature at just under 20.5 Kelvin and the cold at just over 19.8 Kelvin, which is perfect for the region where the liquid deuterium won't freeze nor boil. Finally, in conclusion, the thermosyphon worked, everything flowed in the correct directions, and the helical design that I came up with while I was looking at different hex geometries is now the favored design. So with further research, I was doing all of this in a 1D simulation. The more senior cryogenic engineers working with the Toucan collaboration will be doing this in 3D simulations and using much more advanced commercial software than I have. As well as our Japanese collaborators are actually building these and testing them out. Thank you, and I'd like to thank NSERC, the University of Winnipeg, CIMP, Triumph, and all the Toucan collaborators, and Dr. Jeffrey Martin for making this possible for me to pursue this research this past summer. Thank you.